This is the final section that we will cover in Chapter 9. It's called Taylor and Maclaurin series. Some students absolutely love this because it's basically following a pattern and then identifying the pattern. So some students really enjoy it. So basically, we're going to come up with a procedure that allows us to come up with a power series for all derivatives of all orders. So here is a theorem, the form of a convergent power series. So we've already kind of talked about power series. Now, one thing that I want to point out is that this here refers to the nth derivative. So if you look at what this equals, we are going to have to find lots of derivatives here. So the theorem says that if a power series converges, then the series must be a Taylor series. The converse is not true. So here's the definition of Taylor and Maclaurin series. Basically, they are the exact same thing, except a Taylor series is at x equals c, whereas c is 0 if we're dealing with a Maclaurin series. So really, what this is saying is we need to find the nth derivative at c. So c could be 0, so we want to find f prime of 0, f double prime of 0, so on and so forth. Okay, so really it is just a formula that we kind of have to get used to. So here's the first example. It says use the definition of Taylor series to find the Taylor series centered at C. Well, since this is centered at 0, really I'm going to be finding the Maclaurin series. Okay. And the Maclaurin series, again, is the following. Where this is 0. Okay, so this is just a formula that we're dealing with. Okay, so because we need to find or evaluate the derivative, the first thing we want to do is find the first several derivatives. So I typically find f of x all the way to f triple prime. So the third derivative. So we were given f of x, it's e to the negative 4x. So I can then find the derivative of this. Now be careful that you're finding the derivative and not the antiderivative. So this is negative 4e to the negative 4x. Remember, you keep it and then multiply by the derivative of the exponent. So then f double prime is equal to 16e to the negative 4x. And f triple prime is then equal to negative 64e to the negative 4x. Now you can keep going with these derivatives, but really the purpose of doing this is just so you can set up the first several terms of the series. Now, once you have these, you want to evaluate these at c. And in our case, c is 0. So we are going to find f of 0, then we will find f prime of 0, f double prime of 0, and f triple prime of 0. Okay, so plugging in 0 here, I have e to the negative 4 times 0, which is e to the 0, which is 1. Plugging it in here, I have negative 4 e to the 0, which is anything to the power of 0 is 1. So this gives me negative 4. Here I have 16e to the power of 0, which is 16. Then here I have negative 64e to the power of 0, which is negative 64. So we are looking for the Taylor series. So we are looking for something that resembles this. We're looking for a summation. So now that I have this, I can go ahead and start plugging this in and seeing the first several terms. Okay, so e to the negative 4x is equal to, now, this first term here, this is f of 0 divided by 0 factorial times x to the 0. Okay, so if you want to put it all in, you can. But this, we've already done this part. This is all done right here in the blue. Okay, so we have 1 over 0 factorial times x to the 0 factorial. That's the first term. So plugging in n equals 0. Then the next term is when n equals 1. If I plug in 1, this numerator is negative 4 over 1 factorial is just 1 times x to the first power. Okay, so now we'll plug in n equals 2. So when n equals 2, we have 16 in the numerator. Then we have 2 factorial times x squared plus n equals 3. That gives us negative 64 over 3 factorial times x cubed. Okay, so we want to see what's happening here. We want to try to identify what this pattern is. So a couple things that I notice is the alternating sign. Now remember, if we have an alternating sign, we can represent that as negative 1 to the nth power. Now another thing I notice is I can put these all over 1 if I want. And then they're in the numerator, so that's one thing we can do. But notice how we got these values, or notice what's happening. Here we have 1, so if this is 4 to the power of 1, I get 4. 4 squared is 16. 4 cubed is 64. So what I'm finding is that if I have 4x to the power of n, I will end up getting this, 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 so on and so forth. And then I also recognize that this is all over n factorial. As you can see, that's what I plugged in. So this here is equal to the sum of this from 0 to infinity. So this here is our Taylor series. Now it takes a little bit for some people to recognize the pattern and come up with the series. So this is just going to take some practice for some. For others, they see it as a puzzle and they really enjoy finding these. You also might be asked to find the center of convergence, which we have had plenty of practice with. Okay, let's take a look at another example. So same thing, the only difference now is we are going to be centered at 2. So instead of a Maclaurin series, this will be a Taylor series because we're not centered at 0 anymore. So recall from the definition, a Taylor series looks like this. This is a derivative at c divided by n factorial times x minus c to the nth power. And if we plug in some values, then this ends up being f of c plus f prime of c over 1 factorial times x minus c to the first, so on and so forth. Okay, so we're going to take the same approach that we did before. The first thing we want to do is find the first several derivatives. Now, we know that f of x is 1 over 1 minus x. And this can be written as 1 minus x to the negative first power. So that might be helpful when we are finding the derivative so we can apply the chain rule. So then f prime is negative 1 minus x to the negative power of 2 times the derivative of the inside, which is negative 1. So a negative times a negative gives us a positive 1 minus x to the negative power of 2. F double prime, now I'm going to find the derivative of this. So the derivative of the outer function, leave the inner function times the derivative of the inner function. So this gives me 2 times the quantity 1 minus x to the negative power of 3. And then we'll find the third derivative. So this gives me a negative 6 times the quantity 1 minus x to the negative power of 4 times negative 1. So I have 6 times the quantity 1 minus x to the negative power of 4. Once we have found our derivatives, then we want to evaluate our derivatives at x equals c. And in this case, it's 2. So first, we're going to find f of 2. So when I plug 2 in here, I get 1 minus 2, which is negative 1 to a negative first power. This gives me negative 1. F prime of 2, plugging 2 in here, I have negative 1 to a negative power of 2. This gives me 1. F double prime of 2, plugging 2 in here, I have 2 times negative 1 to the negative power of 3. This results in a negative power of 2. Finally, f triple prime of 2 gives me 6 times negative 1 to the negative power of 4, which gives me 6. Now again, you can keep going. If you can't recognize the pattern from just these first several that we've evaluated here, you can keep on trucking along. It's completely up to you. So our expression 1 over 1 minus x can be found in the following way. So the first thing we want to do is we want to plug in n equals 0. That's where we're starting. We're always going to start with n equals 0. So when that happens, if I find f of 0, or I'm sorry, f of c, this becomes our very first term here. Okay, so f of c we found right here. So our first term is going to be negative 1. Then plus, now we're going to apply the formula here. Okay, so up on the top is what we have here. So this is when n equals 0. This will be when n equals 1. So I have the following. All right, so f prime gives me 1 over 1 factorial times x minus 2 to the first power, plus, then I have negative 2 over 2 factorial times x minus 2 quantity squared, plus 6 over 3 factorial. So this is n equals 2, n equals 3, times the quantity x minus 2 cubed. And then this goes on, and I want to figure out what this is equal to, what this sum, how this sum can be represented. Okay, well, once again, we have alternating signs. Okay, if we have alternating signs, generally speaking, we will have something like this. Okay, so now we just need to figure out what else we end up with. So I want to point something out. Let's look at what we have. Well, this becomes 1 over 1, and this cancels. 2 factorial is 2 times 1, which is 2. This also cancels. 3 factorial is 3 times 2 times 1, which is 6. This will also cancel. So you will find that these coefficients will all cancel, leaving you only with this piece. And the only thing that changes is the exponent. So this becomes x minus 2 all raised to the nth power. And this here is our Taylor series. Done. On the next slide here, it talks a little bit about convergence of Taylor series. You can go ahead and take a moment and read through that. It would be helpful for you to watch some of the CalcView videos on this just so you can see some more examples. Here it talks about some guidelines for finding a Taylor series. I've already gone through that. The only thing I really haven't gone through are showing you the interval of convergence and talking about that. But it's all the same thing we've done before. If you watch the videos on CalcView, they'll show you how to do that. I don't think it's asked in your homework, however, that's why I skipped over that part. Now, there is another little something that we will come up with, and it's something that's very common. It is a binomial series. A binomial series takes on this form where x can be some number. And if we expand this, we will end up with this. Okay, so it's just kind of like a famous type of series. Okay, so we are going to use this to come up with some sort of Maclaurin or Taylor series. And here's an example. It says use the binomial series to find the Maclaurin series for the function. So we want to use what was listed on the other page. So sorry, give me a second to write this here. Sorry, I appreciate your patience. My goodness, what happened there? There we go. Okay, and this just keeps going. All right, so this is the binomial series. Okay, so, all right. Now, if we are looking at this formula, if you will, we need to identify what k is in our problem. And since this is in the denominator, we can rewrite this like so. Pardon me. Where k equals -4. So all we're going to do is plug -4 into this formula. That's it. So let's do it. Okay, so first we have 1. K, so anywhere we see a K, we are going to replace it with a -4. Okay, so then our next term is minus 4x plus, we have -4 times -4, I'm just going to do it all together. -4 minus 1 is -5. All over 2 factorial. Oops, don't forget the x. Plus -4 times -5. Pardon me. Times -6. All over 3 factorial times x cubed. If you need some more terms, go for it. But let's simplify this and see what we have. So 1 minus 4x. A negative times a negative is positive. And I'm going to leave this as 4 times 5 over 2 factorial times x squared. Then over here, a negative times a negative is positive, times another negative gives me a negative. I'm going to write this as 4 times 5 times 6, all over 3 factorial times x cubed. Okay, so we want to see what's happening. We want to see if we can come up with some sort of summation that summarizes what we've just found. So let's see here. Again, we have some alternating signs. We have a fraction, so that's one thing that we might want to consider. But we need to figure out how we can write these things. Now this is n equals 0, n equals 1, n equals 2, n equals 3. So let's just kind of write down some things that we're noticing. I'm noticing that we will have a -1 to the nth power. I'm also noticing that I have x to the power of n. Okay, but then I also have something that I'm noticing here and here. Well, to me, this kind of looks like 6 factorial or 5 factorial, right? Because this would be 5 times 4 times 3 times 2 times 1, but there's some stuff missing. And then here this would be 6 times 5 times 4 times so on and so forth, but there's some stuff missing. So how can we represent these factorials? Okay, but notice some things are missing, right? So what happens is these factorials end up canceling some things out, and you end up with the following. You will have n plus 3 factorial in the top over 3 factorial times n factorial. And again, we're going to multiply this by x to the nth power. Oops, and then we have n equals 0 to infinity. And again, this will take a little bit of playing to figure out where this comes from. So just kind of play with it, watch some more examples, and it will become easier to understand. Now here, there is a basic list of very common power series. So these are the series that come up most frequently. Okay, so all of these. And it's going to ask you in some questions to use this chart in order to come up with a Maclaurin series for the function. Okay, so it also gives you the interval of convergence, which is nice if you are asked for that. So it says, find the Maclaurin series for the function. Use the table of power series for elementary functions on the other side, on the previous slide. So here we have the natural log of 1 plus x cubed. Now, I'm sorry, I can't go back on here for some reason. If you look at the previous slide, this is really close to the natural log of x. The only difference is we have a little something more than x. Okay, so from the table, this is what I have. So from the table, I know that the natural log of x becomes x minus 1 minus the quantity x minus 1 squared over 2 plus the quantity x minus 1 cubed over 3. I'll give a little bit more here. Okay, and then generally speaking, here is the formula that this, I don't know what happens over here, is derived. Okay, so one thing we can do is we can call this g of x instead. Okay, so we'll say, hey, let this be g of x. Okay, so g of x is this. Well, if this is g of x, we will want to find g of 1 plus x cubed because this is what we are evaluating here. So anywhere I see an x, I am going to replace it with this. So it's just algebra. We're just going to plug stuff in. All right, so when I do that, I have 1 plus x cubed minus 1. Oops, let's do the natural log first. Okay, so plugging this in, 1 plus x cubed minus 1, then 1 plus x cubed minus 1 squared all over 2 plus. I think you can kind of follow along without me saying what is going on here. So negative 1 to the n plus 1. This is 1 plus x cubed minus 1 to the nth power all over n. Okay, so now let's see what happens. Looking at this, these ones cancel, 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 right? Doesn't look like anything else cancels, so let's see what we get. So this is equal to, so this, maybe I'll come over here, x cubed minus, this gives me x to the 6th over 2. Plus, this gives me x to the 9th over 3. Minus, this gives me x to the 12th over 4. Plus, over here, I have negative 1 n to the 1st power times x to the 3n all over n. This is my Maclaurin series. So I have used the table, followed the pattern, and so I didn't even have to come up with the Maclaurin series on my own because I was able to use the table. So the natural log of 1 plus x cubed can have a Maclaurin series representing it in the following way. There you have it. Oh, I forgot the sum, sorry. There you go. Sorry about that. Enjoy. I suppose I should point out that we're starting with 1 here instead of 0, because if we plug 0 in, we will get something that's undefined. Okay, let's look at another one. G of x is equal to 2 sine of x cubed. So we are going to compare this to sine of x from the chart. So from the chart, sine of x is equal to, this is directly from the chart. You might want to print that off or have it in your book, like bookmark that page, because it will be something you're going to refer to quite a bit. Okay. Okay, so now in our case, so we're going to say, hey, let this be g of x. Okay. Now in our case, we have 2g of x cubed, because instead of x, we have x cubed. We also have a coefficient of 2. So this will be equal to 2 sine of x cubed. And now we're going to plug everything in. I need this 2 on the outside. Okay. So anywhere we see an x, we are going to replace it with an x cubed. So we have x cubed minus x cubed cubed is x to the 9th over 3 factorial, plus x cubed to the 5th is x to the 15th over 5 factorial, minus x cubed to the 7th is x to the 21st all over 7 factorial. Okay, now you come here. You have -1 to the nth power. Instead of x, we are going to use x cubed to the 2n plus 1 all over the quantity 2n plus 1 factorial. Now, sometimes in these problems, you can come up with this formula. If you want to distribute this, you can. But sometimes, oh, and then you can distribute this too if you want. Several different types of the answers will be accepted. For example, for this one, even if you just write several terms instead of this, that's accepted also, because that is still a Maclaurin series. So you could write this and you will still be good. Okay. So there you have it. I think I have one more example for you. Okay, so this one, it says find the first 4 non-zero terms of the Maclaurin series for the function by multiplying or dividing the appropriate power series. And then it says use the table of power series to help you out. Well, okay, here's what's happening. We have 2 functions in one. We have e to the x, and we have this natural log function. So basically what we're going to do is we are going to use the tables for e to the x and for the natural log of 1 plus x. Okay, I put a star there because really it's just x. And then what we're going to do is we're going to combine these and see what happens. Okay, so let's take some baby steps. From the table, e to the x is the following. And it's nice that we can just use e to the x without having to make a substitution. We get this 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial. And then we can generalize it by saying x to the nth power over n factorial. Okay, so that's just directly from the table. We're going to do the same thing for the other one, but instead of the natural log of x, we're going to use 1 plus x instead of x. And when you do that, you get the following. X minus x squared over 2 plus x cubed over 3 minus plus, and then generalize it here. Okay. All right. So what we are doing is we need to multiply these. Okay. So what I'm going to do is I am going to line up like terms. Okay. So I'm going to line everything up. So first we have, writing this stuff in blue, and I'm going to expand the factorials. So I will have 1 plus x squared over 2 plus x cubed over 6 plus x to the 4th over 24 plus x to the 5th, and I'm going to go out to the 6th term. Now we need to try to get the first 4 positive terms, and because that's what we're asked to find. And oftentimes if you go to 6, that's enough. Sometimes you need a little more, sometimes you need fewer, but that's a good starting point. Okay. Now I'm going to do the same thing with the natural log, but I'm going to line them up. So since I am starting with x, I'm going to put it below here. So I have x minus x squared over 2 plus x cubed over 3. Now notice the like terms are lined up. Minus x to the 4th over 4 plus x to the 5th over 5 minus x to the 6th over 6. Now this is just one way in which you can set this up, okay? But we are multiplying these, okay? So since we're multiplying, what we're going to do now is we're going to take everything in here and we're going to multiply it. So I'm going to take this first orange term and multiply it by every blue term. Then I'm going to take this and multiply it by everything. And I want to be very organized when I do this. Okay. So, and it's going to take a lot of space. So I'm going to try to write small. So I have x times 1, which is x. X times x is x squared. X times this will give me x cubed over 2 plus, wait a second. Yeah, okay, so I suppose I can line these up. This isn't really lined up very well. Okay, sorry, I'm starting over. So this gives me an x, taking these, sorry. Then this will give me an x squared. I suppose, I don't know what's better. It doesn't matter. I kind of like the first way a little bit better. I'm sorry. Okay, so trucking along, x over 2 plus, then we have x to the 4th over 6 plus x to the 5th. So this times this over 24 plus x to the 6th over 120 plus x to the 7th over 720. Okay, so now we're going to take this and do the same thing. Okay, so we're going to take this times this. Well, this is going to give me a negative x squared over 2, so I'm going to write it right here, keeping these lined up. Then I have a negative x cubed over 2 minus x to the 4th over 4. Sorry, right here. Then minus x to the 5th over 12 minus x to the 6th over 240 minus x to the 7th over 1440. Okay, so keep on going. Now we're going to go here. Multiply it by everything. When I multiply this by 1, I get x cubed over 3 plus x to the 4th over 3 plus x to the 5th over 6 plus x to the 6th over 18. And you can keep going, but I am not. So I want to show you what's happening here, okay? I need the first 4 positive terms. So I'm going to be adding these together, all right? So this adds to be x. That is positive. When I add these, when I add these, I also get a positive. Now here, these end up canceling, but then this is positive. Now here, when I add these up, these all cancel out. So I need to keep going. Okay, so if I keep going, oops, there should be one more there, sorry. Okay, so now if I multiply these, this will cancel. This times this will cancel those out. Sorry. Okay, so now I'm going to take this times this to get what we just canceled. This times this to give me a negative x to the 5th over 4 minus x to the 6th over 8, so on and so forth. Okay. I can keep going, but I will run out of room. And in fact, I think I should do a little bit more over here. So plus x to the 5th over 5 plus x to the 6th over 5. So we need to find the first 4 terms that are positive. We end up with x plus x squared over 2 plus x cubed over 3. And then when I add up these here, I end up with plus 3x to the 5th over 40. And this will give me my first 4 non-zero terms. And that wraps up section 9.10 in chapter 9.